So I'm recording this session now. So this is an Archer 2 training course. I'm very briefly going to overview how this works. And I've already... Fine, so the Archer 2 training course, very brief overview. Okay. So Archer 2 is the new UK National Supercomputer Service. It's managed by the UK Research Councils and EPCC. It's housed, operated and supported by EPCC, and it's a crate machine. And as part of supporting that service, we run a lot of training, which is 60 days per year at various locations. Of course, various locations at the moment means from our homes, and it's free to all academics. And this course is actually free to everybody. The new machine will look something like that. This is the machine we're going to use for the practicals. It's a very large national machine, but of course this course is completely generic. This MPI course will run on any computer, your laptop to the world's largest supercomputer. Just happens to be we're using Archer 2 for the exercises. We have a small system already installed. The main system should go live in a couple of months, and that's a picture of the current system. Lots of wires, and it's being installed. But what our system we're using is about a tenth of the final. About a quarter of the final system that we're using. This is another machine Cirrus we're not using. What is EPCC? Well, we're the closest thing that the UK has to a national supercomputer centre. We've been around since 1990. Originally, we were called the Edinburgh Parallel Computing Centre, hence the acronym. We're a centre of excellence at the University of Edinburgh. We've been around for a long time, running national services since 1994, over 100 full-time staff. We do a whole range of research, commercial projects, teaching and HPC training. And if you go away from this course and you say, well, I'd like to work with EPCC, get in contact, we can join together on academic proposals. European proposals, of course, are going to be a bit more of a problem going forward, but a lot of our staff are named research associates on collaborative research grants, and that's how we get involved with at least the academic collaborators. Normally, you'd be at a course at a physical location, and you might be in Edinburgh. So this is Edinburgh, a very nice picture of Edinburgh. We're in the centre of town, just off to the left here. It's a lovely city. It's a shame people can't visit at the moment. I thought I'd show a picture of it. We're up there in the north, well, in the middle of Scotland, as you may know. These Archer 2 resources you probably won't need. Hopefully, this isn't a course about Archer 2. It's a course by MPI. So hopefully, all the information I will give you is shrink wrapped, but that's where the information is. My name's David Henty. I'm in charge of education and training at EPCC, which includes our MSc, our PRACE training centre, which I'll mention later, courses on the Archer 2 training programme and commercial training, and my own research is around parallel programming models, accelerators and performance, generally looking at parallel scaling and performance issues. Other resources, please fill in the feedback form. You'll be sent a link at the end of the course. If you have inquiries about Archer 2, go to the help desk. I'm going to plug our MSc. We run a one-year postgraduate taught masters course, which has been running for almost 20 years. And you were probably not interested in that, but some of if you have students or other collaborators, they might be interested. It's now available online as well. This is some of our students from previous years, but I won't dwell on that. I just thought I'd mention this. I'm going to mention PRACE in a minute, but as part of PRACE, we developed a supercomputing MOOC, which is at this URL. It's free. You can pay to upgrade, but it's there for free. It's very conceptual, no computer programming required, so it's probably not relevant for the attendees of this course directly, but again, it might be relevant for people you work with. It used to run as a set period of time where we supported the students with providing educators, tutors. It's now available all the time in a self-study mode. So I just thought I'd say that was another thing we developed under PRACE. Hopefully that might be interesting. During the course, you've got personal accounts for the duration of the course. We'll give you machine access for maybe up to a month after the course, but they will be deleted afterwards. So take copies of all your work. I'd recommend you do it towards the end of the course. Don't worry about the course materials. All the slides, exercises will be available on the Archer 2 website. We have an archive. They'll just move to the archive site, so don't worry about access to the materials. This isn't relevant. I normally say the room we're in isn't secure, but your security is your own issue at the moment, unfortunately. We have a code of conduct which we like you to behave to adhere to. This might look all very obvious. You know, when would anyone not show courtesy and respect towards other community members? But you'd be surprised. So, you know, I have been taught on courses. The main thing is to realize that people have different experiences. Some people on this course will be very experienced programmers, other people will not be so experienced. So, you know, other people have not great knowledge of one field and not of another. So please be open and help each other. And we have an instant reporting form if you feel there's been any bad behavior, but all the detail is up there. If you're in the UK, you would be able to, if you go away from this course and think, well, that's great, but I'd like to apply that to my own work, I'd like to work on developing my own parallel code or improving its performance, we run something that's only relevant to UK people, I think, but something called the ECSC, which gives funding to develop and optimize codes for Archer 2. That's all part of the Archer 2 service, and there's the URL there. So just very briefly, I said this is actually a PRACE course. It's part of our PRACE training center. So I want to briefly say what PRACE was. PRACE has 26 members. The UK is represented by EPCC on behalf of the UK research councils. And of course, the UK status in PRACE. We're a fully active member of the current PRACE project, which runs for about another year. What happens beyond that with Brexit, who knows? But this is all the members. And as part of that, PRACE has funded 10 training centres. And we've been with a training centre since the very start, along with these other centres. And if you're interested in the pan-European training, which is all being offered online at the moment, this is the central URL. PRACE funds delivery for courses. It also funds catering and such like, but you're not getting that. If you're interested, our upcoming training is here, along with the PRACE. Again, please fill in the course feedback form. Because this is a PRACE course, there'll be a PRACE feedback form, but you will get reminder emails containing the link. So please fill that in. I mean, feedback's very important. We take it very seriously. Good feedback is great. We can go to the PRACE and EPSRC and tell them how wonderful we are. But critical feedback is also important because we do review it. We do review all the feedback and we try and use it to improve the courses. And the feedback is by default anonymous. You can leave your identity if you want to be contacted, but by default, the feedback is anonymous. So I hope you enjoy the course, and please enjoy questions. Please ask questions. You know, I know it's difficult with these online courses, but you know, most people find it easiest to ask questions in the text. We can go to voice if you want, it's fine, but actually, but initially, I would encourage you at any time you have a question, just type it into the chat box. I will get a notification and I will try and answer it as soon as I can. I would rather, all the slides and the material are up on the web. I would rather spend the time I'm lecturing discussing problems you're interested in, not just going through the slides. So in terms of, that's really all I wanted to say there. Are there any questions at this moment? I just wanted to just to be sure we're on the same page in terms of materials, I will share my so you'll have seen is that coming? Yes, you'll all have seen the Archer website. If you go to training, upcoming training, you'll see this course, message passing program with MPI, and this is the main page. The timetable, what I've done this time, I've run this course in various formats. We're still experimenting, so that people don't get completely overwhelmed, I've decided to run it with a couple of days in between. So I'm doing Wednesday, Monday, Wednesday, not 3 solid days, which I think people found rather tough. You will have access to the machine in between because you have your own personal account, so that gives you time to do the practicals. I've also decided to, In the face-to-face version of this course, I have 4 hour-and-a-half sessions where each session is lecture, practical, break, lecture, practical, break. I think the last time I ran this course in that format, it was awkward for some people. So I've decided this time to go lecture, lecture, practical, lecture, lecture, practical. So, you know, the standard, it's slightly different on the first, but the standard format is that we'll do lectures from 9:30 to 11, and then normally it will be practicals from 11:30 till 1, then lectures from 2 till 3:30, and then practicals from 4 till the finish. I won't be able to be around for most of the practicals, but I have colleagues, 2 or 3 colleagues who will be here to help you. The disadvantage of that is we have quite a lot of lectures, you know, in the first session. I will do a break between the 2 lectures, but the advantage is I think it gives people more freedom and time to engage in the practicals. So we'll see how it goes. You are all welcome. So, okay, so the material is actually stored. We have a course chat where you can put type things in. It might be interesting, for the moment, it would be interesting maybe So, I mean, this is going to be open for the whole time, so it might be useful if people could go to that link and you know, and type things in. I'll check it later on and we can see what people are interested in. The course materials are on a separate GitHub, and basically all the slides are here. These are the lectures I'm going through, and there's also exercise material here. And the first exercises we'll do will be purely conceptual. We won't be logging onto Archer 2 until about midday. So you will have had emails about applying for an account. So please apply for an account if you haven't applied for one already. And then, okay. So I was just going to start off now with, I thought I would maybe do just to get to know people, a little bit of a quiz. So this is not, so I'm going to have some problem with this. I'm going to do a few little quizzes, and hopefully this works, but the quiz interface isn't brilliant in Collaborate. It's quite a good system, but it'll take me a few seconds to get this quiz going. Apologies for the delay, but I can't set quizzes up in advance in this system, which is very annoying. So you should be getting a poll now, just asking where you're based. Be useful to know where people are based. Quite a few responses. If people could type, that would be useful. So I'll show the responses now. Okay, so we have mostly people from the UK, a couple of people from Scotland and England, and then we have 5 or 6 people in it. Okay, that's interesting. I now wanted to just get to know what your interests are. So I will, or your background. So I'll just apologize. I am sorry that it takes a while to get these polls going, but I can't cache them, so I need to set them up, unfortunately, as we go along, which so I've seen a question there. I'll answer that in the chat just in a second. Okay, so so apologies. That limits the number of responses. So I also wanted to put in a response of working for a company or other. So apologies, it didn't let me. I didn't realize it's limited to 5 responses. So apologies if you're working for a company or another position. I wasn't able to give that option there. So so while we're filling that poll in, there was a question from somebody. Are we going to cover the difference between open MPI and proprietary MPI, and what is how it works to compile a wrapper? In some sense, yes. In some sense, no. I mean, the answer to that question is, if I was giving, imagine this course was a program on C. Imagine this course was a course on programming in the C language, yeah, in C or C++. I wouldn't care whether you're using GCC, Intel C, I don't know, Microsoft C++. I don't care. C, C++ is a language. And same as MPI. I do not care what MPI library you use. They're all MPI. It's a generic portable standard. So you should not care whether you're using OpenMPI or we're going to use Cray MPI here or MPI CH2. Really makes no difference. I really don't. I'll cover briefly how it works, but I really don't, it's not something to be concerned about. It's a very good question. It's a very good question. But luckily, it doesn't matter. Okay, so we have quite a lot of PhD students and research assistants. Apologies, I didn't give the full gamut of options there. And a final one is just to find out about your language choices. This is in terms of programming language, obviously. So for this course, so the second one's supposed to be C++. So the response here is C, C++, the whole shebang, C++, okay, basically C with C out instead of printf, Fortran 90 or Fortran 2008. So I'm interested. So I don't care what language you're using, C, C++, Fortran, MPI works for them all, but I would just be interested to know what your preferred choice of language for this course is. I do provide solutions, simple solutions, so you can look at them, but I'd just be interested in what people are. Okay, so there's people doing C++, people doing no one's C++, but basically C, and most people are sort of Fortran 90. So that's useful to know. That is very useful to know. So I'll cover all these issues briefly at the start. Yeah, okay, that's useful. Actually, I should show the responses here. Sorry, so you know. So that's useful to know. Okay. Okay, thanks everyone. So if we now I will go on to the I think that's really all I wanted to know. That's given me a useful. So now what we're going to do between now and 11 is I'll give a brief overview of the concepts of MPI, then maybe a little break, and then I will do a thought experiment which will take us up to 11. We won't start actually logging on to Archer 2 until midday, or maybe until midday for the first exercise. But if you have had any particular problems logging on to Archer 2, which you think and getting your account ready, then the coffee break from 11 is a time maybe to address them. But I'll leave the logging on issues for the moment, and I'll start doing the conceptual lecture. So give me a second here. I'm having to switch between different windows here, which is giving me slightly sorry about this. I'm just losing my windows slightly here. Okay, so if I now this course has a long history. It's been around since the early 90s. I've been in charge of it quite a while, but I'm just going to give credit to all the people that worked on the course. All our material is under license, and the licenses are explained on the website. So what we're going to cover is we're going to cover message passing concepts, basic MPI programs, point-to-point communications, and modes, tags, and communicators. That's a slight technical detail. That will be the first day. The second day will cover more advanced things, non-blocking communications, collective communications, virtual topologies, and derived data types. And then the final day will be really focused around a case study, which is on image processing. And I'll give a short lecture on MPI design, tips and tricks. But hopefully with having the lectures spaced out, you'll have a chance to absorb the information in between. So the aims, it's a practical course to teach you to understand. So there are two concepts. One is to understand the message passing programming model, the message passing model for parallel programming. And the other is to write parallel programs in C, C++, or Fortran using the MPI library. And there are lectures and notes, but most importantly, by writing and executing an example MPI program. So it's really important that, that's, to engage. If you really want to learn, you need to write. Even writing simple programs gives you a very, very, can give you very interesting information. What's the motivation? Well, the MPI library is the most important piece of software in parallel programming. Now, you might say, I would say that given that I'm running the course, but 99.9% of the cycles on parallel supercomputers across the world are used with programs that use the MPI interface. That is the dominant, has been for several decades. That's how you write parallel programs on large supercomputers. That's why it's still very important. There are alternate models, but most of them actually are complementary or built on MPI. So understanding MPI is really fundamental to understanding large-scale parallel programming. I think writing parallel programs using MPI is fun. So that was really a very short overview. And now I'll give the first lecture, which is going to be purely conceptual. So what I'm going to do is I'm going to give this lecture, then we'll take a 5-minute break before I give the next lecture, just so you have some time to recuperate. And again, please, at any point, type in questions, and I will take them during the course. I do get a little notification that there's been a question, so that's very useful. So, message passing concept. So, this lecture will cover the message passing model. What is the model we're using? How should I think about my parallel computer? How are we going to write programs? Something called SPMD, single program multiple data, which is the model that MPI and most message passing systems have used. Communications and collective communications, and this is all at a conceptual level. So just to take imagine this was a course on programming. Imagine you'd not programmed before, okay? You'd never written a program in any language before. This was your first programming course. And that's serial programming as opposed to parallel programming. There would be 3 levels I would want to talk about. The first thing would be concepts which are independent of programming language. We have arrays, subroutines, variables, control flow. A program is human readable. We might have object-oriented concepts. Those are concepts which are independent of a programming language. Then I might say, okay, for this course, we're going to learn to program in Python or C or C++ or Java. and we're going to have things like if, then, else, and structures. Okay, that would be the languages. But say I picked C. Then there are various implementations. You might be using the GNU compiler, or the Intel compiler, or the Cray C compiler, or the Portland Group compiler. So there are these three levels: concepts which are independent of all programming languages which are standards, and compilers to implement them. Now, we're going to talk about message passing parallel programming, and there are those three levels. We're going to talk about the concept, and we're going to talk about processes, send and receive, SPMD, collectives and groups. We'll talk about all these things. But the nice thing about message passing parallel programming is when I then go say, well, it turns out that these message passing is implemented through libraries. You don't have any choice, which is a good thing. You just learn MPI. So you don't have this question of, well, I want to learn programming. Should I learn Python, Java, Fortran, C, or C++? If you're going to do message passing parallel programming, you learn MPI. Now, if I'd been giving this lecture 25 years ago, or even 25 years ago, there would have been several libraries in this box. But MPI has become completely dominant. That's great for you guys. It means you only have to learn MPI. But it is important that you think at this level. When I write a program, I don't think about if, then, else, structures and things. A serial program should be thinking, what are the arrays in my program? How am I going to store variables? What are my classes and objects going to be? How am I going to structure my program? You should be thinking at a high level, and then say, okay, how do I implement that using Python, Java, Fortran, or C or C++? You should be doing the same with MPI. You should be thinking at the conceptual level, what are the sends and receives I need to do? What collective calls do I need to make? And then implementing an MPI. So you shouldn't think of this as an MPI course. I like to think of it as a message passing parallel programming course using MPI. But although there's one definition of the library, as someone mentioned earlier, an earlier question, there are implementations, which is good. There are free implementations called OpenMPI, Intel have MPI, Cray have their own MPI, IBM have their own MPI, there's something called MPI CH2. Okay, so that's interesting. Now at this point, I want to do another quick poll because I have a question I want to ask. So there's a way of doing parallel programming called OpenMP. We run courses on it. I wanted to know what OpenMP is a way of doing shared memory parallel programming using threads to do parallel programming within a single computer, multi-core node. Okay, so that's interesting. Most people have heard or are aware of it. So what I wanted to say at this point, okay, that's very interesting. So that's very useful information for me, thank you. Maybe 20 years ago, people decided they were going to write an open implementation of MPI, and they called it OpenMPI. That was a really stupid thing to do, because people get confused about OpenMP. And although OpenMP and OpenMPI are both ways of doing parallel programming, they are so different you couldn't imagine it. OpenMP is a way of getting your compiler to parallelize your program using threads on a shared memory computer. OpenMPI is an implementation of the MPI library, nothing to do with the compiler at all, a library which allows you to do distributed memory parallel programming. So just be careful, OpenMP and OpenMPI are completely different. And unfortunately, the naming convention causes a lot of confusion. So I just thought I'd mention that here. So message passing, the message passing model is based on the notion of processes. So when you run a program, okay, you write a program, you run it, you launch an operating system process. And you can think of a process as an instance of running program together with the program's data. And what we do in the message passing model is parallelism is achieved by having many processes cooperate on the same task. Now, each process only has access to its own data. All variables are private in the OpenMP sense, but processes communicate with each other by sending and receiving messages. Now, multiple processes is nothing new. This computer I'm logged onto at the moment is probably running hundreds of processes, okay? Lots and lots of them, okay? I mean, actually, if I'm on Windows here, I can, maybe it's easier if I do that here. If I turn on Task Manager, which is which one here, this one here, we'll see that this computer is running huge numbers of processes. What's it running? It's running lots of stuff, hundreds and hundreds and hundreds and hundreds of processes. All of these is a separate program running on this computer, okay? And that's nothing new, right? A computer running multiple processes is nothing new, okay? Computers do that all the time. But the important point about MPI is it allows us to run multiple processes, but not have them working on their own, but collaborating on the same task. What we want to do is to take, we don't want to run lots of independent problems. We want to take a simple problem and solve it faster by running it on multiple processes at the same time. And the way that that is achieved is that processes in the message passing model communicate with each other by sending and receiving messages, and we'll talk about what that means later on. But typically, these are library calls from a conventional sequential language. People have invented lots and lots of parallel programming languages over the years. None of them has ever really taken off. People hate learning new languages, and so it turns out that the way that people has been popular to do parallel programming and message passing in particular is just to say, okay, you can program in C, C++, or Fortran, but I'll give you a library which gives you extra functionality. So the sequential paradigm, when you run a sequential program, you launch an operating system process, which you can see in your, if you're on Linux, you can see in Top, or you can see in your task manager. And you think of your program as having exclusive access to a processor and its associated memory. Now, that isn't really true. Modern operating systems can schedule and deschedule processes all the time. But importantly, if that's your model, if you believe that when you run a program, it becomes a process and it has exclusive access to a processor and some memory, that's a correct way to think about it. You will write correct programs if that's your model. The parallel programming model for message passing is very similar, except we run multiple processes. We run, say, 4 processes. And here then I've numbered them 0, 1, 2, and 3. And that turns out to be what MPI does. MPI numbers your processes from 0 going up the way. But the important point is modern operating systems try very hard to make processes, independent programs, independent from each other. They make them completely ring-fenced from each other. It means that if you write a program and it crashes or scribbles off into memory it shouldn't have access to, it doesn't crash your computer or your other processes. Modern computers, modern operating systems try very hard to make independent processes completely independent from each other, ring-fence them. That gives us a problem in message passing because by definition, we want these processes to talk to each other. But we do that by calling the message passing interface. If we want 2 processes, 2 independent programs to talk to each other, we call an MPI routine, and that interfaces with the communications network. And MPI takes care of all the details. I don't care if it's an Ethernet network or an InfiniBand network, or maybe even Wi-Fi, okay? As long as there's a network, MPI will interface with that and deliver the messages. It's like if I send an email to somebody. I don't care if the email goes over 5G, 4G, Wi-Fi. I don't care, it just gets there. So the whole point about MPI is it insulates you from the hardware, allows you to write parallel programs which are portable to different computers which have different communications networks, but it allows you to write a portable program, and that's one of its major goals. And so this is easier if we're in a physical training room. We're not, of course, but what we're trying to do is you want to run a single imagine we were teaching in a workstation cluster in a teaching room like this. We have lots and lots of workstations. Your model is you want to run a single computation. You want to solve a single problem. You might want to simulate the weather or the airflow around an aircraft or the spread of COVID-19 or something. You want to run a single computation across all these workstations in the room. And MPI allows you to do that by running different programs or copies of the same program on all these workstations but MPI allows you to talk to each other because these will be connected by some network, some wires. Okay. Now, in practice, we're going to use a dedicated parallel computer, but actually that's the best model for an MPI program. A cluster of workstations in a training lab, and I'm going to run a process or multiple processes, different programs on all these computers, and MPI allows me to tie them together. So a very good question here from Eric. If the two processes are on the same node, do the messages still pass through them? So no. So modern MPI implementations are clever. They will recognize that two processes are on the same node, and they will do the communications through direct memory copies. And one of the exercises we do is a ping pong, where you just throw messages between two processes, and you will be able to see that it's quicker. Two processes talk to each other quicker if they're on the same node than if they're on different nodes. You can actually measure that. So that's interesting. That's a very good point, but you can measure that experimentally. Clearly, it's much quicker to just copy memory on a node, because remember, the confusing thing now that these computers, these workstations, all have multiple CPUs. Okay, so this isn't a sync. This will have multiple CPU cores. That's the confusing thing about modern hardware. Even your laptop is a parallel computer, and that's a very good question. So did that answer your question? We'll be able to look at that experimentally. So what we're going to target are distributed memory architectures. This is a picture of a previous supercomputer we had called Hector. It's just a nice color. But what we have is we have a bunch of processors. The physical architecture, how we build large parallel computers, is quite dumb actually. We just buy lots. It's completely analogous to this picture here. Okay, we just buy lots of computers and stick them together with a network. So a modern large distributed memory computer is lots of processors with their own memory, all independently, but they're tied together with an interconnect. And the difference between a supercomputer and a network of workstations is you pay a lot of money for a very fast interconnect. And of course, you don't have keyboards, terminals, and screens for all these computers here. But architecturally, a modern parallel supercomputer is no different from this. A whole bunch of workstations all running their own operating system to get connected together by a network. It just happens to be they're more tightly connected and maybe more efficiently put together. The confusion nowadays is each of these computers is actually a multi-core CPU like your laptop. And so a generic, your good conceptual model is a connection of multi-core laptops connected together by a network. So what we say, just some terminology, in a supercomputer sense, each laptop is called a compute node. Okay, so as Eric said, if two processors are on the same node, what he meant is if two processors are effectively running on the same laptop. Each laptop has its own operating system and network connection. So this was our supercomputer. Okay, your best model is 5 multi-core laptops. If each one was a quad-core laptop, the total system would have 20 CPU cores. But the slightly confusing thing, and MPI actually ignores this, but from an architectural level, the confusing thing about modern computers is if they have 20 CPU cores, that's not 20 nodes each with 1 CPU. It's something like maybe 5 nodes each with 4 CPU cores. And actually Archer 2 that we're going to use at the moment, each node has 128 CPU cores. So that is a good, that's your conceptual model. When you're running a parallel program, a collection of multi-core laptops connected by a network, and each of these has a name: laptop 1, laptop 2, laptop 3, laptop 4. My PC, your PC. We'll see the same, that each of the nodes has a name. But a node is effectively a standard computer with its own memory, but it's multi-core. So we're going to talk about communication. How does communication work? So we have two processes, process 1 and process 2. And think of these as running on different nodes. One of these processes is running on my laptop, the other one is running on somebody's laptop in Australia. Okay? And what we want to do is we want to communicate data from process 1 to process 2. Okay? When we write a parallel program, we're going to split the computation up between different CPUs, between different processes, but at some point we're clearly going to have to exchange information between them. They can't operate completely independently. And so process 1 has a statement A equals 23. And that sets the value of A equal to 23 in process 1's data. But of course, process 2's data is completely separate. Process 2 is running on a laptop on the other side of the world. So how do I communicate the value of this A from process 1 to process 2? Well, what I do is we see that the message passing library MPI gives us a magic function call. So we can say send. We'll see what I'm going to say. I want to send my value of A to process 2. Now there's various analogies for this, but a good analogy is sending an email. So what would happen there if this was an email analogy is that that data would go into process 2's inbox. The reason it doesn't go straight into process 2's memory is that if this is my laptop in Australia, I don't want someone with a laptop in Edinburgh to be writing into my own memory. That thereby, process 1 is not allowed to access process 2's memory directly. Process 1 can't scribble across process 2's memory. The memory of a different process is isolated, and that's obvious if you think of this process I'm running my laptop here in Edinburgh, and this process running in Australia. And so for this to succeed, okay, so I might take the email analogy, okay. I'm emailing some data, so I'm here in Edinburgh. I send an email to my colleague in Australia. Does sending an email transfer data from my brain to my colleague's brain? I want to communicate from my brain to my colleague in Australia. Does sending an email, I've sent an email, communicate that data from my brain to her brain? I want to go. So I've sent an email. Has that communicated the data to my colleague in Australia? Can I assume that she knows what I sent? Exactly. That's Helen. Not unless she's read the email. And that may seem like a fairly straightforward observation, but it has the important consequence in message passing is that process 2 has to actively issue a receive. So sending data in message passing is a two-sided process where the sender actively sends, which is like sending the message, but the receiver has to actively receive, has to actively issue a receive call. Unless she reads the message, nothing happens. So it's only at this stage, once the receive is issued, that the data appears in process 2's memory, and process 2 can then decide. Process 2 has entire control over its memory. Process 2 is saying here, I want to receive data from process 1, and I will then put that data in my variable B. So on process 2, B becomes 23. Then process can do something to do A equals B plus 1, and process 2's A value can be 24. And this is the confusing thing about message passing programming. Process 1 has a variable A, process 2 has a variable A, but they're totally different variables. This variable A is in my computer in Edinburgh, this variable A is in her computer in Australia, and it can have a different value. So this is going to be potentially quite confusing, but this diagram, which is very, very simple, really encapsulates the important points about message passing, okay? If I want to communicate data, the sender has to actively call a send and say where it's sending it to process 2. The receiver has to actively call a receive. At that point, the data is received into process 2's memory, but process 2 decides where the data goes, and process 2 has decided here that the data from process 1 will go into its variable B, and process 2 can have a variable A, which has got nothing to do with process 1's variable. It can do A equals B plus 1. So is that clear? It's actually, it's quite simple, but it is important to understand that. Now, the obvious question now is what happens if process 1 issues a send and there's no receive, or process 2 issues a receive and there's no send? We'll cover all those details later. Okay. So the other thing is that imagine I could, if I had wanted to run on 100 processes, write 100 programs. However, that becomes very awkward. And in scientific and technical computing, it turns out that in most of the time, most of the processes are doing the same thing. And so most message passing models have used, and MPI does use, the single program multiple data model. You only write one program, but all processes run their own copy of the same program. Each process has a separate copy of the data. So that's you write one program, but you run multiple copies of it. You might say, if I'm running the same program, why doesn't each process do the same thing? Well, there's only one thing which makes these programs different. Each process has a unique identifier. In MPI, when you run 100 copies of the same program, as soon as they come alive, one will be numbered 0, one will be numbered 1, one will be numbered 2, up to 99. And within the program, you can say, what number am I? And based on that, you can follow different control paths through the program depending on your process ID. So just because you're running the same program doesn't mean you're doing the same thing, because you can say, if I'm process 0, print hello. If I'm process 1, send a message to process 3. Okay, so they can do, but it's just a convenience. We write one program, but run multiple copies of it. Now, MPI doesn't talk about the hardware. MPI talks about processes. But in real applications, we typically run process per processor core. So if we were running an MPI program in this situation, we have 5 quad-core laptops, I would typically run 4 processes here, 4 here, 4 here, 4 here, and 4 here, because each of these has 4 CPU cores. I could run 8 processes here, 93 here, 5 here, 1 here, and 27 here. Nothing to stop me. But why in real scientific and technical computing do we run 1 processor per processor core? If I've got 5 nodes each with 4 cores, I will run 20 processes with 4 processes on each node. Why? There's no reason functionally, but why would I typically do that? Why wouldn't I run 8? For performance exactly, job, but why wouldn't I run 20 processes on each node? I mean, I could, but what would be the problem there? So yes, it's not scaling well. So what happens if you run multiple processes? If you run more physical processes than CPU cores, then the operating system context switches. Exactly. Okay. So that's what modern computers do. I'm running hundreds of processes on this computer. They're not all running at the same time. The operating system is switching them about, which is great. For laptop multi-core computing, that's what you want. I'm running an email client. When it's not running, it can be parked. But for scientific and technical computing, we're only interested in performance. So you could run 8 processes on a 4-core CPU, but it wouldn't go any faster. In fact, it would probably go slower. So when you're developing a program, the fact you can run more processes than physical cores is great. I've got a 4-core laptop here. I could run an MPI program with 20 processes to debug it on my laptop. Great. But for performance, we run 1 process per CPU core. You might say, well, actually, that's a bit crazy, because a standard model in parallel computing is a task farm. We have controllers and workers. So you have one process, which is the controller, call it me, and I send work out to you guys. You might say, well, clearly I need 2 programs there. I need a controller program to control things and a worker program to do work. Or you do an MPI, you put them in the same program. You have one main, and you say, if I'm the controller process, I call the controller function, else I call the worker function. So really, if you want the processes to do different things, you just make them functions and stick them in the same program, and the same in Fortran. So I've mentioned messages, but I haven't really talked about any detail. A message in MPI transfers a number of data items of a certain type from the memory of one processor to the memory of another. And I mean, basically in MPI, a message is a fairly basic thing. You should think of an MPI message as being 5 integers, 6 double precision numbers. It is not a class or an object. Now, there are ways of doing that, but fundamentally, MPI is designed for scientific and technical computing, and more modernly, you can use it for data science analysis, obviously, where you're sending data. So a message in MPI is fundamentally 20 double precision numbers. The message has more information than that. It might have who sent it, where it's going, what the type is, and how much there is, but the fundamental payload is the data itself. And so a message, and the important concept we have in MPI is we have different communication modes. And the one thing I'll mention here, and we'll come back to this, but it's a conceptual thing, is sending a message can either be synchronous or asynchronous. And we'll have this choice in MPI. Synchronous send is not completed until the message has started to be received. An asynchronous send completes as soon as the message has gone. So I'll come back to, I've got some analogies in the next slides. Receives are usually synchronous. The receiving process must wait until the message arrives. And these are best illustrated by examples. Now, I like this diagram because but in fact, this is a very old example. The analogy, synchronous send is like faxing a letter. Basically, in the old days, when you faxed a letter, you went to the fax machine, you put a fax in, and you waited, and then you waited for the beep from the machine, and you knew the letter had been delivered, and you left. Possibly a more useful example for you guys is making a phone call. Making a phone call is synchronous. You pick up the phone, you dial the person, and you wait until they pick up the person picks up. So so making a phone call is synchronous. You wait until the person picks up. You may wait forever. Okay, so that's conceptual. The other way is asynchronous send, and that analogy is posting a letter. You stick a letter in the letterbox. You only know when the letter has been posted, not when it has arrived. Or analogously, sending an email. So fundamentally, making a phone call and sending an email are different modes of communication. Making a phone call is synchronous. You wait for the other person to pick up, and therefore you know the data has been received. Sending an email is asynchronous. You hit send and you never know if it gets there. And we'll see in MPI, we have both synchronous and asynchronous sends, and which one you want to use depends on the context. So we've considered point-to-point communications here, one sender, one receiver. It's the simplest form of message passing, and it relies on matching send and receive. And there's an analogy. So the advantages of asynchronous are if you do synchronous communication and the person never issues a receive, you wait forever. Whereas with asynchronous, so with synchronous, there may be delays where you wait for the person to issue the receive, where you're doing nothing, or if they never issue the receive, you may wait forever and your whole program falls over. Asynchronous is a fire and forget model. Now, the difference between synchronous and asynchronous, I have a whole lecture at the end of today which discusses that. But that's the potential advantage of asynchronous, is that you don't have to wait around for the process to issue a receive, and also you won't deadlock. You won't wait forever if they never issue a receive. Does that answer the question? But it's an interesting question. We'll come back to a whole lecture about that. MPI recognizes that in scientific and technical computing, we often want to do collective communications where we communicate with a bunch of processes. And these can be built from simple messages, but they're implemented separately. So MPI has both point-to-point communications with a sender and a receiver, and collectives, which involve a whole group. And so there's a barrier in MPI, which is a global synchronization, where we all wait until we move on. That can be useful in some situations. A more useful one is a broadcast. I'm doing that at the moment. Okay? Broadcast is a one-to-all communication. So this can be useful at the start of a program. One process may read in some data, but you want all the processes to know how big is our arrays, how many iterations are we going to run for, how big is our time step. You might read that in on one process, but want to broadcast it everywhere. You could do that with lots and lots of separate point-to-point communications, but it's more convenient and more efficient to issue a broadcast. So data starts out on one process and is copied everywhere. The important point about this is, in MPI, in message passing terminology, at the moment, we are all participating in a broadcast. We are all participating in a broadcast. It just happens to be that within that broadcast, we have different roles. I am sending data and you are hopefully receiving it. So all processes will participate in a broadcast, but within that, they will have different roles. And we'll come back to that routine later. So a broadcast is from one process to all others. If one process had the data 8, I would broadcast it and that would be copied to everybody. A scatter is a bit like a broadcast. We'll come back to all these in MPI, but you scatter data. So you have an array 0, 1, 2, 3, 4, 5. A broadcast would copy that data everywhere. A scatter splits it up. So with a scatter, one process gets 0, one gets 1, one gets 2, one gets 3, one gets 4, one gets 5. And you might want to do at the start of a program, you might initialize an array on a controller process and want to split that array up, give a different piece of the array to all the worker processes. And you can do that with the scatter, or at the end of a program, you may do a gather. You may say, right, we've all finished our calculation. I want to write the data out to disk. I'll just do that through a controller process. We'll gather all the data together so I can write the data out, and that's called the gather. Actually, by far the most common operation is a reduction operation. We combine data from several processes to form a single result, and that's like taking a vote. Okay, you might say, are we going to have a strike? You all have a vote, yes or no, but then we have one global answer here where there is no strike. Or in science, often what you want to do is take an average. So all of us here have our age. I'm probably the oldest person, but anyway, we all have our own age. But if I wanted to compute the average age, I would need to add all the ages together and then divide by the number of people. So a reduction operation takes distributed data, ages, and combines them to form a single result. And so to compute the average age, I need to combine them with addition. But you might want to know who's the oldest person. You might do the maximum or the minimum. So and a reduction operation takes distributed data, our ages is a good example, and combines them together to produce a single result, say the max, the min, or the average. And they're very, very useful in scientific and technical computing, where you've distributed the calculation, but you want to form a single result. So you form a global sum, product, max, min, etc. from distributed data. Here I'm adding it, 0 plus 1 plus 2 plus 3 plus 4 plus 5 is 15. So before I finish this lecture and we have a quick break, just to go through the concepts, when we launch a message passing program, and we'll do this in practice on Archer too, we write a single piece of source code with calls to message passing functions such as send and receive. We compile with a standard compiler, GCC, Intel CC, Cray CC, Intel Fortran, whatever you want, and we link to a message passing library provided for you, which implements these functions. And there are open source ones like OpenMPI and vendor supplied ones like Cray MPI. You then run multiple copies of the same executable on a parallel machine. Each copy is a separate process. Each has its own private data completely distinct from the others. And what's confusing there is each copy can be a completely different line in the program. So debugging parallel programs is hard. The two questions you'd like to ask are, what is the value for my variable A, and what line of the program am I on, are both meaningless in MPI. You have to say, what is the value of A on process 57? What line of the program is process 23 at? So that will become difficult. And to launch a parallel program, we're normally given a launcher program. It's typically called MPI run, where you say, please run n copies of my executable called program.exe. You don't have to log onto each machine and run the program by hand. For convenience, there'll be a launcher program. But all the launcher program does is launch multiple copies of your executable. Issues, send and receive must match. There's a danger of deadlock. If you issue a receive and there's no send, your program will stall. And so receives in MPI are synchronous in the sense if you issue a receive, it's like standing by the phone and waiting for a phone call to come in. And it may surprise you, but in MPI there are no timeouts. So if you write an incorrect program where a process issues a receive and there is no matching send, that process will stall and wait forever. So that's the major problem in MPI. Unless you match your sends and your receives, your programs don't work. It's possible to write very complicated programs, but actually most scientific codes and data processing codes have a simple structure, and it often results in simple communications patterns, which can be implemented often in collectives, and you should use collectives wherever possible. So summary, messages are the only form of communication. If you're not issuing a send or a receive, you're not communicating. Your process is just running like a normal program. All communication is explicit. Most systems use this SPMD model, single program, multiple data. All processes run exactly the same code, but each has a unique ID. Processes can take different branches in the same codes. And the basic communicators form is point-to-point, send and receive, which we'll see can be synchronous or asynchronous. We'll come back to that. But connective communications exist for more complicated patterns. Summary 2, message passing is a programming model. It's a way of thinking about parallel programming, but it's almost universally implemented in MPI. MPI is just a library of functional subroutine calls. It's essential to understand the basic concepts that the variables are private. If you have a variable A and you run 50 copies of your program, there are 50 A's, one on each process. All communication is explicit, and we have single program, multiple data. Although we run one program, there are multiple instances of that program, each with their own private data. And actually, although the syntax for MPI can be a bit complicated, the major difficulty most people have is understanding the message passing model. So that's why it's very important to write your own programs and make mistakes. That means that you start to understand the model. It's very different model to sequential programming. So just to finish this final lecture, I'm only a few minutes over. This is a perfectly, in some pseudo language, this is a perfectly decent piece of code in norm. I've got a value x. X is I'm writing a weather simulation, okay, and x is the rainfall. So each process computes the rainfall, and if the rainfall is negative, there's no problem. Okay, so in your sequential program, see if x is less than 0, if the rainfall is less than it, print error and exit. Okay, that's fine. Why is that a dangerous piece of code in a parallel MPI program? Anyone think why that's a dangerous thing to do? So in a sequential program, we have one value of x. If it's less than 0, my process quits. Fine. What's the danger? Yes, so Matthew, the other processes may not exit. That's exactly right. Why? So exactly why might it not apply to all the processes? So you're exactly right. It depends on the value of x. Exactly. X can have different values. Okay. X may have different values on different processes in general. So actually, terminating a parallel program is quite a difficult thing to do. What you would have to do here is you might, for example, do a reduction operation and compute the minimum value of x, and then exactly. So the 2 points to the two close call points are that the value of x will be different. Some processes will let. So if some processes quit and some processes don't, then your whole program will probably deadlock. So if only part of the processes sign off, Giovanni's answered, what will happen is sometime later, I will expect an email from that person. I'll issue a receive and I'll never send you a message. Your program will probably deadlock. Okay, so probably what will happen is that process will stop running, the other process will carry on, and sometime later your process will deadlock. So it's a real problem here. Yeah. So understanding that program is a dangerous program to write is actually one of the key concepts in MPI programming. So what I will do, I think, is we'll take a minute break and come back at 10:45. I'm talking GMT here, but we'll take a 10-minute break. I'm then going to give a short lecture which talks about conceptual issues, and I'm going to introduce a model, a traffic model, which I think is a very useful conceptual model for thinking about parallel programming, and it's a useful one to have in the back of your head. I'm going to briefly go through some solutions to this traffic model just to pick out the key aspects. But I think the main thing is to have this model in your background, in your memory, when we talk about various other MPI concepts going forward as a way you could actually apply it. So we've talked about these update rules. We've been through this already. And I've talked about the state cable. And this was the pseudocode I left you with. And there's a number of ways you could parallelize this model. Okay. So first parallelization strategy you might consider doing, this is something people did many, many years ago when parallel computing first came about, is you might say, well, I'll give everyone an entire copy of the whole road. So you broadcast the data to two processes. Now, I'm going to use a test case of just two processes here in a road of length 8. It's really a bit too small, but it's the biggest thing I could draw here. So what we do is we broadcast the data to two processes, then each split the calculation between two processes. And that's trivial to do because every process has all the data. So the first process just does this calculation. the second process does this calculation. But then at the end, we have to globally resynchronize all the data after each move. This is called a replicated data strategy, where you give every process has a complete copy of all the data, but is only responsible for updating a subset of that data. And then you have to basically, after you've done any updates, you have to do a global resynchronization. You have to resynchronize the data across everybody. And if you think about it, that's not a very efficient strategy, because each process is doing a small amount of work, and then we have to resynchronize all the data. Everyone is sending data to everybody, and so this strategy rapidly runs out of speed on any more, in this particular case anyway, on anything other than a few number of processes. So although this was the kind of thing people did in the very early days of parallel computing, replicated data, give everyone a copy of the entire data structures, it's not something which is commonly used now, because it doesn't scale very well to large numbers of processes. So what we want to do, of course, is want to split the data up, and I've already shown you how to do this in my little diagram of phoning each other. So we scatter the data between two processes. It's a distributed data strategy. So the important point is, we noted that the internal cells can be updated independently. All the cells except the boundaries can be updated independently, but we must communicate with neighboring processes to update the edge cells. So to update the value of this cell, I need to know what the value of this cell is. And the nicest thing to do is to declare an extra value here. We call them halos or ghost cells, to store the copy of that data. Now, we did that in the serial code to cope with the boundary conditions, but there we just copied data in. Here we'll use that, you will use communicated data to go in there. And we also must, the number of, to compute the total, the average velocity, we need to know the total number of moves. That requires communication. So you split the calculation between two processes. Each process must know which part of the roadway it's updating, and we synchronize each completion of each iteration and obtain the total number of moves. Now, I haven't talked about, in terms of parallelization, load balance is not an issue. What I mean is that if we have a road of length n, load balance is making sure that each process has the same amount of work to do. The very naive way I've written the code, updates take equal computation regardless of the state of the road. So we split the road into equal pieces of size n over p. So if we have a road of size 15 and 3 processes, each one gets 5. We then, the rule for cell I depends on cells I minus 1 and I plus 1. An important observation is the interior cells, in general, the n over p minus 2 interior cells can be updated independently, but the edge cells are updated by other processes. So we have to have some communication there. So we need communications to get the value of the edge cells from other processors and to produce a global sum of the number of cars that move. And so what we do here, the correct way to do the message passing parallelization is I want to start off with that road and end up with this road here. That would be the correct answer in serial. I have 2 processes and 2 halos. So each process has its own data, the first 4 here and the last 4 here, but we actually extend the road with extra, they're called halos or ghost cells, to receive the data. We then do some sends and receives. I say copy here, but this is actually requires sends and receives to put the data in, which are temporary copies. It then allows me just to run the serial update code on the parallel section, because when I look update upwards from this cell, it should be that value here, but it's already been copied in here, so I get the correct value. And I compute the local number of moves, then I have to do a reduction operation to do the global number of moves equals 3. So by these halo cells are commonly used. Ghost cells are also called in message passing programming. They're there to record the state of the data which you need from other processes. And in this example, and it is typical of many examples, you'll need to copy in a small amount of data from your neighbors. So is that clear? Does anyone have any questions about that? Okay. So as I said, we're a bit lecture heavy this morning, but we're about to go and talk on some actual code. So I'm going to show you, going to talk about MPI, and immediately after that lecture, we'll get onto Archer 2 and start to do some actual programming. So if I so I'm going to give you a brief history of MPI and then the very, very basics of how it works. So what is MPI? Well, in the early days of parallel computing, this is in the late 80s, early 90s, each parallel computer had a different way of doing parallelism, a different message passing library. People got very annoyed about that. And then in the early 90s, the MPI forum was formed. It was a lot of people from the US and Europe, from 40 different organizations, including EPCC, and they decided to come up with a standard. And that was produced in 1993. Although there's been lots of versions of the standard since then, MPI hasn't fundamentally changed since it was first designed in 1993, over 25 years ago. It's been very successful. MPI is a library of function and subroutine calls. It's not a language. There is no such thing as an MPI compiler. When you run your C or Fortran compiler, you invoke the C or Fortran compiler you invoke knows nothing about what the MPI actually does. It will know the prototype or interface of the function calls, but they're in an external library. Your compiler has no idea what MPI is doing. Your compiler thinks that it's compiling a serial program with some funny subroutine calls or function calls. So the compiler gives you zero help in MPI programming. There's no such thing as an MPI compiler. So J. Scott says, presumably other message passing interface standards, how do they compare to MPI? Well, there aren't really any which have, I mean, there were ones historically called PVM. But basically what happened is in the early 90s, there were lots of competing message passing standards, and everyone just got together and agreed on one, and they agreed on MPI. So there aren't really any other MPI standards in active use, because all the ones that had been developed at that time were involved in the MPI forum, and they got to develop MPI, taking the best features, hopefully, of all the ones that have been done before. And since then, there's not really much point in inventing another MPI, another message passing standard, because everyone uses MPI. So that's, yeah, there aren't really any other MPI. There are other libraries for doing communication, more lower level libraries, but not really message passing. If someone tells you they're running a message passing program on a parallel computer, 99.9% they're using MPI. Does that answer your question? Yeah, fine. So the goals and scope of MPI to provide source code portability so that you can write an MPI program on your laptop and run it on a Cray supercomputer, and to allow efficient implementation. Also, it offers a great deal of functionality. I mentioned this, it allows support for heterogeneous parallel architectures. I mentioned this at this point because in principle, some of the MPI calls look very complicated. In principle, MPI allows you to run a single parallel program across a Windows machine with an AMD processor and a Linux machine with an ARM processor and another machine with a with an Intel processor. In principle, MPI supports heterogeneous parallel architectures. So in principle, you can run an MPI program across a bunch of computers where one computer uses 4 bytes as integers and one uses 8 bytes as integers. So there's a lot of support in MPI to allow that to happen. In practice, nobody does that. Modern parallel computers, Archer 2 will have 750,000 CPU cores. Every single one is identical. So in practice, we don't exploit that functionality. But I just mentioned at this point, in principle, it is supported in MPI. Okay, first piece of code, MPI library. You have to therefore include header files, which include lots of prototypes and definitions and magic constants. C++, I'll come back to the fact this doesn't include MPI.h. Fortran 90 use MPI. Fortran 2008 use MPI FO8. You should not be using this. This is very outdated. Now, we should really be using this standard, but for historical reasons, almost everyone who writes MPI uses what I call the Fortran 90 standard use MPI. I will cover what the details are of the 2008 interface tomorrow, very briefly. But in this course, I used the Fortran 90 interface because it is the one which is most commonly used. I will outline very briefly tomorrow. It's quite simple to understand how the MPI or FO8 interface differs, but it's still not commonly used. So I will focus on the Fortran 90 interface. So you should use #MPI.h if you're C++, use MPI if you're Fortran 90. Did I say tomorrow? Yes, I mean next week. Sorry, I said tomorrow because then I'm thinking in my mind that this is a 3-day course day out. Sorry, it's not. You're right. It's next week. Yes. Apologies for that. So MPI functions, all MPI functions in C have the same format. They're capital MPI underscore capital letter, lowercase letter with all the parameters. They return an error code. C being C, you can just ignore the error code if you want. Fortran, for some reason, Fortran programmers hate functions. They like subroutines. So in Fortran, it's call MPI. The capitalization doesn't matter in Fortran, and the error code is an extra variable. The I error is optional in Fortran 2008 version because Fortran 2008 supports overloaded functions with different numbers of arguments, but otherwise it is essential. The number one error mistake that Fortran programmers make is that they forget to put the error code in. We'll cover later why you often may never check it. In C, you can just ignore it because it's a return code. In Fortran, you have to specify the error code as a variable. So this is slightly complicated. MPI controls on internal data structures, and it gives you what it calls handles to reference them. It's a bit like if you do file I/O. In C, you have a file star SP. You have this file pointer. Who knows what's in it? In Fortran, you have a unit number. Okay. Clearly, there's a lot of internal state associated with those things. The C handles are defined type defs. There are different types. In Fortran 90, all the handles are integers. Now, because when MPI was defined back in the early 90s, Fortran did not have user-defined types. That's the major difference. The Fortran 2008 interface is basically the same as the C interface. All the Fortran 2008 handles will come back to what these are later. Are user-defined types as for C. But I will present the Fortran 90 interface here where everything's an integer. It's still the most commonly used. But I mean, if you're a Fortran programmer, you might want to use the Fortran 2008 interface. It's fine. I'll cover how to do that tomorrow on Monday. So initializing MPI, because it's a library, you have to initialize it by hand. In C, it's a rather horrible interface called MPI init, int star argc cast. I'll come back to this later. In Fortran, it's MPI init I error, integer I error. It must be the first MPI procedure called. You can't do MPI unless you've initialized it. But multiple processes are already running before MPI init. As I said, when you run an MPI program, you launch it with a launcher program. This call does not create the MPI processes. They're already created. We'll come back to this when we run some example programs. It's when you launch the program, you create multiple copies. MPI init just allows them to get together and talk to each other. But every programmer has to have MPI init. So how do we use it? So you see this is a rather horrible prototype in C. The reason is that if you have a C program, int argc char star argv, which is your standard C prototype, you pass a pointer to argc and a pointer to argv. And this is historical, but you can imagine a system where, for example, there are two issues here. You can imagine a system where the command line arguments are only available to one of the MPI processes. This call allows MPI to broadcast them to everybody. Or you can imagine MPI passes extra information through the command line arguments, and this allows it to rearrange them. It's slightly a historical quirk, but into argc you pass a pointer to the first argument. It's a pointer to argc. This is already a double pointer. This gives you a triple pointer. That's why this is the prototype. However, most parallel programs don't use command line arguments. They use input file. So it's perfectly acceptable to do this. So most CMPI programs begin int main void MPI init null null. We'll just ignore the command line parameters. But technically, it's worth pointing out if you do have command line arguments, you have to pass pointers to them to MPI init. In Fortran, it's much simpler. Program my MPI program, integer I error. And we will also have had to do the hash include or the use here, call MPI init error, and you can use any capitalization you like here. Now, the most important concept in MPI is the communicator. Every MPI call that does communications takes a communicator. It defines the communications world. It defines the processes taking part in that communication. Now, we'll see later on how to create communicators, but there is a predefined communicator called MPI com world that contains all the processes that are taking part in the MPI program. So, for example, if I launch an MPI program on 7 processes here, they're numbered 0 to 6. We'll come back to that. But MPI com world is predefined to include all the processes which are taking part in the calculation. And so, in any of these future function calls, if you see a communicator argument required, initially we'll just pass MPI com world, okay, because it's a predefined. We will see later how to do more complicated things with these communicators. And so the most important thing you do is, I said that MPI numbers its processes 0 to n-1. So if I launch an MPI program on 7 processes, I say, please run 7 my program. MPI will launch 7 processes. They're numbered 0 to 6. How do you find out what the number is? Without knowing that, you can't do anything. What you have to do is you have to say what the MPI calls this the rank. So the most important thing is, how do you identify the processes in a communicator? Within a communicator, you have a rank. And within MPI com world, which includes all the processes, your rank is a unique integer. So almost what you do is you call the function MPI com rank. You give it a communicator, which is of type MPI com. This is one of these handles, these typedef handles, and you get back the rank. So what this is saying is, what is my rank in this communicator? If you pass MPI com world, you get back a unique integer which identifies you uniquely from everybody else. In Fortran, it's MPI com rank I error is you get back the rank here. This rank's not the physical processor number. It's an internal. It's a logical numbering. MPI logically numbers its processes from 0 to n-1. How this relates to the physical CPU cores in your machine, I don't know. That just depends what happened at launch time. But this is the most fundamental thing you need to know, the rank. So what you do, int rank, MPI com rank, okay, you have to pass, the first argument is a handle of type MPI com, com. What this is defined in the header file, obviously, but we have a predefined one called MPI com world. And then we can do print hello from rank, blah, blah. So that's, that each process says, who am I? So it's a bit weird in MPI. When you're launched, you wake up, this, who am I? This tells you who you are. Am I rank 0, 1 up to n-1? In Fortran, it's just the same. Integer IR, integer rank, call MPI com rank, MPI com world rank IR, print write hello from rank. So that without knowing your rank, you cannot write a useful MPI program. Equally, you need to know how many there are. Okay. In the traffic model, if I need to know my rank to know who my neighbors are. If I'm rank 7, my neighbors are rank 8 and rank 6. So but I equally need to know how many of this there are. If the global rank is size 15 and there are 3 processes, my local road is size 5. So because you're decomposing this road across multiple processes, it's also almost impossible to write a useful MPI program without knowing how many of you are. This is not defined in the program. You don't write an MPI program for 8 processes. You write an MPI program, but then when you launch it, you may decide to run it on 8 processes. And you can inquire how many processes are contained within the communicator. Now, in general, we will see later on how to split communicators up. But if you pass MPI com to MPI com size, you're saying, how many processes are there in the communicator that contains everybody? You're asking there, how many processes are there? So if you launch an MPI program on 8 processes, MPI com size applied to MPI com world will give you back 8. So almost all MPI programs begin in C, for example, hash include MPI.h, MPI init, MPI com rank on MPI com world, and MPI com size on MPI com world. Then you've initialized MPI, you know how many processes there are, you know who you are, then you can get going. Also, you have to finalize MPI into MPI finalize. It must be the last MPI procedure called. And in MPI, you don't initialize MPI, finalize, initialize MPI. You can't reinitialize MPI. What you do is you initialize MPI, you run your program for 5 hours, then you finalize MPI, then you stop. You don't join and leave. Okay, you initialize it, run for 5 hours, and then you finalize it and finish. Okay, so that's a standard MPI program. Hash include MPI.h or use MPI, MPI init, MPI com rank, MPI com size. Do your calculation, which will involve sends and receives. We're going to cover later on. MPI finalize, and then you stop. So that's the very bare bones of MPI. Is that clear to everyone? Does anyone have any questions about that? Okay. So just a few. You might want to know, what machine am I on? Remember, at runtime, these processes are going to be mapped to physical nodes or computers. You might want to know, well, I've got 2 nodes and 8 processes. I wanted the first 4 on the first node and the next 4 on the next node. Has that happened? Well, there's a nice routine called MPI get processor name. It's a very old-fashioned name. It was defined before we had multiple CPU cores. It should really be called the MPI get node name, but it's called the MPI get processor name, where it gives you back a character string, which is just the host name. This is just the host name. So this is a way in MPI of inquiring what the host name is. So now you could say MPI get processor name, proc name, you get back the name length, which you don't care about in C. And then you rank. And in Fortran, it's a character star MPI. This call MPI get processor name, proc name, name error, rank is on machine, blah. So this is just a useful way, we can play around with it, of finding out where the processes are running, which can be useful. Also, we talked about quitting. So the sum is, we've covered some basic MPI calls, but no explicit message passing yet. We'll cover that after lunch. We could still write useful programs. If I had 1,000 files to process, I could run an MPI program on 1,000 processes. Each process could compute its rank, and rank 0 could process file 0. Rank 1 could process file 1, up to rank 999 could process file 999. But so this is how MPI works. But we need to compile and launch parallel jobs. This is not specified by MPI. This is now the details of this next lecture. Hope to take 10 minutes, then we'll actually get on the machine. Gives us machine-specific details. So these will vary. This will not be the same as your laptop, but because I'm assuming that you're using Archer 2 here, I will give you the information on how you compile and run programs on Archer 2. So I have to get that up. I do have it here, sorry. This covers a couple of platforms, Cirrus, which is our other machine, but I'll only cover the Archer 2 information here. So we're going to log on to Archer 2. Hopefully you've gotten applied for an account. You can just use SSH. Log into archer2.ac.uk. There is a complication which because of various security incidents that happened last year, we have higher security on Archer 2 than we used to on other systems, and you require an SSH key. Now, you should have been given in your joining instructions explicit information on getting that working. That can cause issues. As I said, the first practical session is going to start in 10 or 15 minutes, which runs till 1. To be honest, the most important point about that practical session is checking that your login accounts work, and we can help you solve any issues. You can use SSH from anywhere. We don't have IP issues. For Linux, use the terminal plus the command line. For Mac, use the Mac terminal and the command line. Plus, if you want to display graphics, you'll need to install Xquartz. We're not going to be doing graphics till the case study on the final day, but you will need to install Xquartz. For Windows, there's a really nice program called MobaXterm, which means you can use SSH to log into Archer 2 and display graphics. This gives you access to a login node, and there are a few login nodes, and you're assigned to different loads depending on the system load, and the login nodes are shared by all users. Of course, Our current Archer 2 has 100,000 CPU cores. These run a bunch of compute nodes. And on Archer 2, it's a bit of a quirk. MPI programs can only be run on the compute nodes. You have to submit them via a batch system. That's been truncated, unfortunately. So there's a separate document which I'll point you to, which gives you the details, but I'll go through the principle here. So a typical HPC system today is you're on your laptop, use SSH to log into the login nodes where you can upload and download data. To run on the compute nodes, you have to run via a batch system. We use Slurm, which is quite common now, and I've given you scripts to help you do that. Unusually on Archer 2, you cannot run parallel MPI jobs on the login nodes. On most general purpose systems, you can, which makes developing and debugging much easier because you can run a little test program on the login node before you deploy. On Archer 2, we have to run on the compute nodes all the time. Luckily, the login nodes and the compute nodes share disk, so you can transfer a program written here can obviously be run here. I don't provide much source code here in this course. It's very important to write at least once in your life a few MPI programs from scratch. But I have a thing called mpptemplates.tar, which has a bunch of useful files, and you can take a copy of that, and I'll show you how to do that later on and unpack it. Cirrus we're not using, so I'll skip these. Compiling MPI programs on Archer 2. C programmers should use CC. For C++, this is different. This is unusual for Archer 2. On most systems, you compile using things called MPI CC, but here on Archer 2, C programs use CC, C++ programmers use capital CC, and Fortran programs use FTN. Now, there's nothing magic about these MPI compilers. They're really just wrappers around the standard compilers, and they just include all the libraries and header files automatically. The actual compilation is done by a standard compiler. On your laptop, it would probably be GCC or Gfortran. Here on the Cray compilers are Clang, Clang++, and Cray Fortran. But on Archer 2, you always call CC, capital CC, or FTN. Archer 2 is designed for parallel programming. So actually, the default compilers are all MPI aware. That wouldn't be true on your laptop. I provided very simple make files, but you can just compile it in the normal way if you want. I'll show you how to do this later on. Archer 2 idiosyncrasies. It's not possible to run MPI programs directly on the login nodes, so we have to submit to the batch system. The problem is there are hundreds of people using Archer 2, and there could be a substantial delay. So we have dedicated queues for the course for a more rapid turnaround. That's why we've asked you to apply for an account on Archer 2, because the specific training course project we have, where you have accounts, hopefully, has access to these dedicated queues. Outside of the course days, there's a short queue you can use for development. The other weird thing on Archer is that you cannot run from the home file system. When you log in, you're on the home file system. The compute nodes can only see /work, so you have to cd to /work. And I'll cover this in a second. Running on the Archer 2 backend on the compute nodes, we use Slurm. You submit a script that then launches your job. I've provided a batch script called archer2mpi.job, which does. So I can show you how to use the short queue. I can show you that in a second. And this is set up to run in the reserved queue for Wednesday. It requires editing for different programs or queues, and I'll show you that. So it's actually easiest to do this if I show you by. And this is another system which we're not covering. C++, just a brief. MPI is not an OO interface. It can be called from C++. Originally, they supported a proper C++ interface, where I'm not a C++ programmer, so apologies if my terminology is wrong. But you had objects, which were the communicators, and then the calls were methods on those objects. However, as C++ became a more and more complicated language, they gave up. So the C++ interface is now removed. So The interface between C++ and C is well defined. As far as C++ is concerned, MPI is a C library. So it's just as if you're cross-calling to C. So the interface between C++ and C is well defined. The interface between C++ and MPI is well defined. But as far as MPI is concerned, it's just a C library. Documentation, the MPI standard is available online. It's available in printed form, and there's man pages on Cirrus and Archer. You can do man MPI init and get information on MPI init. The message passing standard is a standard. It's not very legible. If you want to buy a book, I would recommend this book. It's very good. It's nothing to do with me. I'm not no conflict of interest. Using MPI, the portable parallel programming with the message passing interface, by 3 of the guys who were involved in the development of MPI, Grop, Lusk, and Skellum. I think that's how you pronounce their name. So if you're going to buy an MPI book, I would recommend that. And so really, the exercise between now and lunch is just the Hello World program. It's exercise 1 on the exercise sheet. It's just to get you compiling and running programs. And so the exercise sheet, which we're going to use now, share a different window. Is course materials. For all the exercises now, I have a single exercise sheet which is down under here, MPI exercise sheet. So this contains all the exercises, and the first exercise is just to log in, write a Hello World program, and run it, and then print out how many processes there are and who you are, just to do an MPI com size, MPI com rank. To try and make things easier, I have a crib sheet which just gives you a run through on how to log on. So what I'm going to do is I'm now going to I'm just going to assume you have a copy of that crib sheet, and I'm going to share a different window, and I'm going to show you how to log on. Hopefully you're able to do this. If you're running on your laptop, I can maybe give you help on how your laptop. Hopefully a number of you, I've approved about 15 or 16 accounts. So here I am. Okay, so I assume I've logged on. That can be difficult. I am logged on to Archer 2. Hostname. It's got you up, but I mean, okay, so I've logged on to Archer 2. I'm in the home directory. That's not any use. I need to go to /work /tao20/tao20, and then my username, which is mine is tao20dsh. If I look upstairs, there's about 15 of us have got accounts here. So now I'm in. Now I need to get this MPP templates.tar. They're stored on the GitHub. Git is a bit weird, and the easiest way it's explained on the sheet is to use wget, and I shall therefore cut and paste that, and I can't. So Git is a bit weird. GitHub is a bit weird, but the way to get the templates.tar is to get. Now what I will do is I will copy so you should also be able to get a copy of that file from /work /tao20/tao20/shared. You should, and that's where the MPP templates. You should be able to get a copy from there. So you should just be able to copy it from there if you want to, or you can use the wget. Now I unpack it, and the program I've given you. There's no MPI note. Let's look at the hello. Oh, are you? Is this showing up correctly? I'm just slightly concerned that it is. I have too many windows open. Yes, it seems to be showing up correctly. If I look at hello.c, all it does is that. Doesn't really do anything useful, but we want to run it, and so we can compile it just by using cc if we want, or if you want to, I can do make -f make file c, does the same thing. Okay, so it's up to you. We now have a program and we want to run it. So archer2mpi.job, this is how you run things. Now, this isn't a course about Slurm. I've given you a script, but if I just show, actually, I want to. And now that color is very annoying. So I'm just going to reset my Emacs. Now in white's much easier. So, and listen. Okay. So we're asking for now the hash s batch commands to tell you what you want. I'm asking for 1 node and 4 tasks per node. That's it. It's definitely that's how Slurm talks about processes. The job name is hello. I'm going to run for 1 minute. I get some output, and this is the magic which selects the reservation. I've commented out for small jobs you do this, which Michael I think has already put into the chat. Yeah, for short queue you do that. If you wanted to use the standard, these are actually commented out. That they're a double hash. That's a commented out. And then we do some magic and we do srun. So apologies, this all looks very complicated, but this is just a template copied from the. All you need to know is that this runs 4 tasks, 4 processes on 1 node. Okay, so let's submit it. Okay, I can do SQ, gives me who's running. It's run already, actually, it ran so quickly because I have dedicated resources, and we get a hello 15894.out, and if I cat that, what do we get? Of course, we get hello world 4 times, okay? What I want you to do is to now compute MPI com size, non-MPI com rank, so it's hello world from rank 0 out of 4. If I want to change the number of processes, I could do 8 tasks per node, okay, and that just runs the same program. It's there, it ran here, and I got 8. Okay, so what do you think happens if I do this? How many hello worlds will I get if I do node equals 2 tasks per node equals 8? How many do you think I'll get? 16, yes. Let's do that. So you can see it says it's running on 2 nodes here. It's running on 2 nodes, and then node 001, 001, and 001. So that's told me what they are. But if I do, it said it's submitted job there. So if I now look at the output, I'm sure it's finished. 158905.out. But of course, some of these were coming from node 001, 001. Some were coming from node 01. I don't know which node these were running on. I don't know what rank they are. So I can find out what rank they are by calling MPI com rank. I can find out there were 16 of us by calling MPI com size. How would I find out what node these ran on? 8 of them were on 1 node, 8 on another one. I don't know where they were. What commands would I use to find out what node they're running on? Anyone remember? I just MPI get processor name, exactly. It's MPI get processor name, and that's one of the exercises I think is to you might ask, how is Slurm distributed these? I told it to run 2 nodes with 8 tasks per node, but our rank, how is it distributed them? Is rank 0 on node 1, rank 1 on node 2, or back? And you can do that by calling it just for fun. So that's really, we're kind of bang on time. Really, between now and 1, I just want you to, you know, just, you know, run these exercises, check you can log in, check you can compile and run programs. I did want to show you though, just for if I go back to my laptop, okay, this is my laptop. Let's do that wget again. Whoops, that was the wrong thing. I'm now on my laptop just to show you that things work everywhere. Unpack it. But on a standard laptop, okay, the standard thing is MPI and MPI run is the standard on a laptop. The architecture is slightly unusual. Or for Fortran, MPI F90 minus O hello hello.f90, and the same MPI run. I get hello world again. That's how you do it on your laptop. So Dehan asked a very interesting, is there a feature to prevent two processes writing hello world at the same time for the output file? So yes, so basically, actually, the MPI run program is your launcher program, or for or on Archer, actually if we cat it, on Archer it's called srun, okay? But you will have a launcher program which within Slurm is called srun, on your laptop is probably called MPI run. And what that does is that program launches your processes, but that program grabs the standard output from each process. So what happens is if an MPI process does a print, it goes to the MPI run program, and MPI run will then output it to the screen. And MPI run is clever. It only ever interleaves things on a line-by-line basis, not on a character-by-character basis. So how the output is intervened, no, it's not gathered. This is all outside of MPI. This is all done. This is all system magic. It's not, you know, this is just my interpretation of what's going on. So conceptually, it's like a gather, but it's really, the important point is that the output, most MPI implementations are good, and they never interleave the output on a character-by-character basis. They interleave the output on a line-by-line basis. But it can be interleaved on in any order. You don't know what order the stuff is coming in, but it will make sure it's not done on a character-by-character basis normally. So that's a good question. It's the MPI run. It's your launcher probe, which is interleaving things on a what am I trying to say? On a line-by-line basis. So that's a good question. Did that answer your question, Dylan? Yeah. So for example, yeah. So if you, I mean, for example, if I, the other thing which is useful, it's oftentimes a bit more fun on a, it's hard to do here, but if I basically, if I make this thing, how do you sleep works? Okay. If I make these processes sleep, for example, let's make them sleep for 60 seconds. Yeah. Yeah. That's a bit long, isn't it? Let's do 20 seconds. Okay, we get that hello world, but now they're all sleeping and we don't see anything happening. And then we'll have to wait for 20 seconds till they all finish. And count to 20. That's a bit long, wasn't it? 1010, 1009. There we go. The interesting point here, though, is if I run that in the background, yeah. So this, I can now look at the I can do it at top, and as far as my you can't even see them actually here. Okay. Well, it's actually running. It doesn't show up in top because they're not using any CPU time. But as far as my operating system is concerned, it's just running 1, 2, 3, 4, 5, 6, 7 copies of my hello program. Yeah. So my operating system, I did a PS. It's running the MPI run, and it's also, as far as the operating system is concerned, I'm just running 7 copies of the hello program. It doesn't know it's a parallel program. Operating systems are very dumb. It just thinks I'm running the same program. Why aren't I? I mean, I'm running multiple terminals. Yeah. If I do it, yeah. I don't. Well, no, I'm not running multiple terminals. That's confusing here. Maybe what are they called? Anyway, but I can't remember what that process is called. But anyway, but as far as the operating system is concerned, I'm just running multiple copies of this executable. Why wouldn't I? The fact that it's a parallel program is sort of into the operating system. And you can see I can run as many processes as I want. I only have 4 CPU cores here, but I can run on 23 processes if I want. Yeah, there we are, running on 23 processes. I'm running 23 processes on my laptop. The operating system is shuffling them all around and doing its stuff. On a dedicated machine like Archer 2, it won't allow you to do that. It will say you're not allowed to run more processes than CPU cores. That's stupid. But on your laptop, it will just do it, which is fine. So that, as I said, we have a couple of helpers who you will see are a number of helpers. Quevin, Michael, and William are all online to help you. So really, this is to get up and running. I don't know if you have any, not all of you have accounts on Archer, but I don't know if you all want to get accounts on Archer. If you're on Archer, I'll just check. I have to. I couldn't forget my password there. I don't know who's on here. Okay, I don't know, but I mean, has anyone managed to log in to Archer 2? I can't see. Okay, and have you managed to run a job? Okay, good. Okay, that's good. That's good. Actually, oops, was I wrong there? Okay, fine. There we have. Okay, so we have, these are the people who are on, a few people on twice. That's fine. Okay, that's good. So we have a number of people. So other people, if you don't have an Archer account, if you don't have an Archer account, then please apply for one if you want one. You're welcome to do these exercises on your local machine, on your laptop. There is a small amount of advice on the website. At the bottom of the page on how to install MPI locally. For Linux users, it's effectively trivial. For Mac users, it's fairly straightforward. For Windows, you can try use the Intel HPC toolkit. I can't give you any advice on that. I mean, for Linux and Mac, it is very, very straightforward to install these locally, hopefully following those instructions. And you can get it locally on your laptop, but that's why we're providing you with accounts on Archer. So there was one user who applied for an account on Archer 2, but they'd used a Hotmail address, and I'm afraid since the security issues, last year, we cannot give accounts to people through Hotmail addresses. So I think I sent an email to that user if they want to get back to me. You can change your email address on the safe. So we require an institutional company email address, something not Hotmail, because we need to be able to sort of at least have some verification that you are who you say you are. Apologies for that, but that's another one of these issues from this. There was a global security incident with HPC systems, affected a lot of systems worldwide. I think it was May last year, and we've had to change a lot of security procedures based on that. So are there any other questions? We're taking a break now, but as I said, we'll have helpers, Queven, Michael and William around until 1, and the next lecture will start at 2. And again, what will happen be more standards after a lecture from 2 till 3:30 with a break in between, and then from 4 till 5 will be a practical session. And what we'll cover this afternoon is the core of MPI, which is MPI communication with send and receive. And unfortunately, in MPI, send and receive are not quite as simple as you might think they are. So it is a large percentage, I don't want to give you a number, but a large percentage of people who use MPI don't actually understand how MPI send and receive work, because it's not quite trivial. So it is a very important lecture to get your head around. But of course, we have exercises to back it up. Okay, so I will stop the recording now.